and today I will give a brief overview of converting waste heat to electricity with inorganic materials. Let's start by looking into what is waste heat. Now, this may sound strange, especially here in Finland. Half of the year, heat is very valuable here, not waste. And even in summers, we can store heat in these big rock caves by storing warm water there and using it in the winter. But in global scale, waste heat is actually a big problem. It's not so cold everywhere, and we are losing lots of energy. Let's see. Let's start by looking into waste heat in the energy sector. This chart here shows how different primary energy sources are used in the United States. It's from last year. The reason I chose United States is that it's the largest economy in the world. This also reflects the global situation quite nicely, and they have excellent statistics available. Good. So, what can we see from this chart is that, first of all, one obvious thing is that actually still majority, 3/4 of the primary energy sources are fossil, petroleum, natural gas, coal. And what is common, especially for these fossil fuel sources, is that we convert them to useful work by burning them. Okay, now the sad fact is that during this process, over 60% of the original energy content in that fuel is actually lost as waste heat. To give a concrete example, in a car with a combustion engine, you drive using gasoline, 20% of the energy, original chemical energy in the gasoline, goes to the wheels, moves you. 80% goes to the air as exhaust fumes. So we are losing 80% of the energy in that case. And 60% in general of the primary energy is rejected as waste heat. This is terrible loss in global scale. Now, how could we harvest some of that energy back as an electricity? Let's say if we could take even 10% of that 60%, it would mean massive amounts of CO2 reductions. Now, thermoelectric energy harvesting is one way to tackle this issue. In thermoelectric energy harvesting, we have a source of waste heat, like we are burning coal. Okay, and some of the heat is, we cannot use it for example, producing electricity. But that waste heat we could direct into these so-called thermoelectric generators, where the other side is hot because of the waste heat. The other side is colder. And because of this temperature difference, the thermoelectric material in between can convert this temperature difference into electrical power output. Nice. This phenomenon has been known for a long time. Materials have been around for 60 years. They are used in niche applications. The problem is that the materials are not good enough to make this large scale in such a way that it would have global impact. Okay, but people are working hard on this, also in Aalto-University. Several research groups are working on this topic. But I want to focus today on a different kind of waste heat source. And that is waste heat in data centers, or in general in computing and telecommunication. Now, data centers like this, these are at the heart of our, let's say, digital life. If you run a Google search, it's a computer in a hole like this that does all the hard work. If you use your mobile phone and do something with it, then typically there's actually some server in a data center doing the actual work. Your mobile phone is just showing it. Okay, and as a result of that, computing nowadays uses almost 10% of electricity in global scale. That's a big number if you think about all electricity used in the world. So, in other words, data centers convert electricity to useful work, the results on our screens, but also waste heat. Let's look into this. So at the heart of every computer, there's the brain of it. So the microprocessor or a graphical processor. And what they are doing is they take in electricity, they do the work, the computing, and then they produce fluctuating heat flows. Not a constant waste heat flow, but fluctuating heat flow. Temperature in a microprocessor can vary tens of degrees in seconds. Okay, now, again, some of that waste heat in certain locations, like in Finland, we can actually utilize. We can warm homes with waste heat from data centers. But again, in a global scale, that's not possible. That's not a solution, and not all data centers in the world can be in Nordic countries. They should not be. So, how can we tackle this issue, or how could we? One solution could be this pyroelectric energy harvesting. So the idea here is that we have a fluctuating heat input. So it's varying all the time, the temperature, like in a microprocessor. And this kind of heat input, if we can direct it to so-called pyroelectric material, this material, with this fluctuating temperature, it is changing its electric properties, so-called polarization. So when it's cold, it's a bit more positive on the other side. When it's warm, it's a bit less positive on the other side, and so on. But effectively, this fluctuating heat input, we can convert into electrical power output. That's the main outcome of it. Well, sounds good. Why don't we have this in all data centers on top of microprocessors? Well, the problem is that the materials are not good enough. So that's what we are trying to improve. Better materials to make this solution for this waste heat problem. Good. So let's look into inorganic materials and what we are trying to do there. In inorganic materials chemistry, this is always the starting point. This is the periodic table of elements, and this is it's an old invention, 150 years and so, but still, on our daily work, it's every day that I look at this table, and it still gives me insight. Good. Now, when we are designing new materials, new pyroelectric materials, for example, a big issue nowadays is that we should focus on elements that are abundant, so widely available in Earth's crust, and non-toxic. So we would like to avoid elements like lead or other heavy metals. Good. So those are some boundary conditions. And as a result, we typically would like to stay on the upper half of the periodic table, where we can play with elements like silicon, aluminium, iron, sodium. We can find those in just normal rocks or sand. So those are ideal materials for the work. Good. So, what about pyroelectrics? What kind of materials can we then use as pyroelectrics? I'm taking here just one example. We have to a little bit look into atomic level. Here's a prototypical pyroelectric material. It's called barium titanate. The idea here is that inside those blue octahedra, we have titanium atoms. The red atoms are oxygen atoms, and green ones are barium atoms. This was discovered in the 1940s, and it's an okay-ish pyroelectric material. In real-life applications, what is used nowadays is this material called lead zirconium titanate. And already you can see from the colors there's a difference. The colors mean that there's now more complexity in the material. So we have substituted some elements with the others. And the main problem is that there's lead. So we would like to get rid of that. Now the great thing about this perovskite framework is that it's basically endlessly tunable, the composition, the chemical composition. So we can change any of the atom type to some other atom type just by designing it carefully and doing the synthesis. So basically, there's an endless amount of variability, and this is at the same time it's a blessing and a curse. So there's lots of possibilities. The whole periodic table is on our use, and we can make any material out of it. However, at the same time, this is impossible to do experimentally in the laboratory. Takes weeks to make the material, to characterize it, so on. So you could do not so much in a year, let's say. So this is where materials modeling comes into play. So we can use computers and computational methods to study materials that don't even exist yet. And we can rule out the poorly performing materials and focus the experimental work on those materials that perform well. Good. So materials modeling, it's a subfield of computational chemistry. So this is my toolkit. These are my methods we use. The idea is that we always start from atomic level structure. And when we know that, and we can study also materials that don't really exist yet, we can just guess the structure. We have the structure, we put that in a black box called quantum chemistry. So in practice, it's a computer and codes running on that. But I'll put it here as a black box. And one equation, don't be afraid. That's the only equation. Okay? And from that box, what we can get is all the properties of the material. For example, electrical conductivity, thermal conductivity, and of course for us, pyroelectricity is what we are interested in, and many more things. Good. So those we can predict just from the atomic level structure, and the beauty of it is that we can always go back. So in a sense, I put in one structure, I get its properties, I know that I want to improve it somehow, I can go back, change an atom, how did it affect, and I can repeat this loop as many times as necessary. Good. And only in the end, when we have reached a material composition that we are satisfied with, we can give it to the experimentalists for further work. So, of course, in this work, we need supercomputers. So in a sense, we are producing waste heat ourselves. But we still think that we are part of the solution, not part of the problem. It's very little compared to what you are, for example, when you are Googling. All right. And I'll finish with this. So what we are really doing at the moment, what is the state of the art? Where are we now? So the key here is that just a few weeks ago, this paper came out. We have now the first ever method that we can actually predict the pyroelectricity of certain perovskite type materials. So we have the first possible method to study a case where fluctuating heat input comes to the material. This makes atoms move in a certain way, and we can calculate what would be the pyroelectric effect from that. And now with this methodology, we can now take that guideline that's always in our use. So with this method, we go to the periodic table and we start playing with compositions that have not been studied before for pyroelectricity. Because people just thought that, oh, it's too much work. But now we can do it with computers. And in the end, let's say, not in weeks, not in months, but in years, there will be kind of recipes for our experimental colleagues to do synthesize novel pyroelectric materials, and eventually, in many more years, to have them in maybe in those data centers, for example. Good. So I will conclude with this, and thank you for your attention.